Hello class, welcome to today's lesson. Before we start, I wanted to just let you know kind of what we have planned for the rest of the school year. We actually only meet, I think, 9 more times. So the next 4 times will be regular lessons and we'll have one more assessment. And then after that, I have planned for 5 review days. So I've picked 5 of the most important topics that we do during the year for your success in pre-calc next year. And we're going to focus on those during review days. So to start today's lesson, it's going to be easiest for you if you get this handout printed, and you're also going to want a graphing calculator. Yesterday, any calculator would do, but today you're going to want that graphing calculator. And let's start with a warm-up. So using what we reviewed yesterday with arithmetic sequences and series, go ahead and try that now, please. Okay, so for how we can tell this is arithmetic, it's because we're adding the same number every single time. So we're adding 3, we're adding 3, we're adding 3. The next term would be 17, then 20, and then so on. So if you're adding the same number every time, it's an arithmetic sequence. This is the formula for the rule for the nth term. And if you plug in your first term and your common difference, you can leave your formula right here, or you can distribute the 3 and simplify to get this version. Either one is fine. And when you go to find the sixth term by plugging in 6, you can plug in here. You'll have 3 times 6, which is 18, plus 2 gives you 20. Or if you plug in 6 here, you're still going to get 20 as your answer. Now, one thing I want to take a moment and show you is this was from chapter 1, way back when. And I want to show you, using Desmos, why this showed up in chapter 1. And if we think about this rule, this a sub n equals 3n plus 2, if we look at the term number and the term value that we have, the first term was 8, the first term was 5, the second term is 8, the third term is 11, and so on, because it's a sub 1, a sub 2, and your fourth term is 14. If I take you over to Desmos and we graph those points, what you might notice is they kind of line up like a linear function. So if we think of this a sub n rule instead as y equals 3x plus 2, so instead of a sub n, think of it as a function with y equals, and instead of n, think of an input x like we're used to. So if we think of this as y equals 3x plus 2, that line will actually go right through those points. And the other point we found was 6. The sixth term was 20. If I plot 620, that ends up on the line as well. So the reason this topic of arithmetic sequences and series showed up way back when in chapter 1 is because we were reviewing the basics before we got really into the algebra 2. We were reviewing like lines, linear functions, and they do relate. They're not exactly the same thing, but they relate, and that's why it showed up back in that section. Now, let's continue on and start to get into today's work. So the first thing in today's lesson is to introduce and discuss geometric sequences. So we're going to be looking at geometric sequences and series. So a geometric sequence is when you not add, but when you multiply by the same number every single time to get to the next term. That's how you're going to know you have a geometric sequence. It's a different kind of sequence. So here's some examples and some non-examples. This sequence is geometric. That's my first term, second term, third term, fourth term. And I can tell it's geometric because it's times 3 every single time to get to the next term. And I don't actually know off the top of my head that 18 times 3 is 54. But since this was times 3 and this was times 3, if I just go ahead and check that, sure enough, 18 times 3 is 54. So the pattern holds. This is called my common ratio. So this one's geometric and the common ratio is 3. We use R to denote the common ratio. This one's geometric. What is R for this one? What are we multiplying by every single time to get from one term to the next? It's -2. So your common ratio can be negative, and if you're multiplying by a negative every single time to get to the next term, notice that the signs alternate. So we had a positive. When you multiply by a negative, you get a negative. When you multiply this by a negative, you get back to a positive, and so on. So if your common ratio is negative, the signs are going to alternate. And down here, when you look at this one, this is also geometric. You might think, oh, I'm dividing by 2, dividing by 2, dividing by 2. But instead of division, we want to think, what are we multiplying by? So just turn that around. We are multiplying by 1/2. If I cut 1 in half, I get a half. If I cut a half in half, I get a fourth. So if I multiply by 1/2, I can get to the next term. So these are all examples of geometric sequences. These over here are not examples. And just to clarify why they're not geometric, when you look at this one, there's different things you might observe. Some of you might notice that you're adding 3 and then 5 and then 7 and then 9. You're adding odd numbers that are increasing. Or some of you might look at this and say, oh, that's 1 squared, 2 squared, 3 squared, 4 squared, and 5 squared. You're both correct. It's just different ways to look at the sequence. But either way, I think we can agree that is not geometric. We are not multiplying by the same thing every time to get to the next step. Now, for this sequence, one way to look at it is that you're multiplying by 2, and then multiplying by 3, and then multiplying by 4. And then if you do 24 times 5, you get 120. So this sequence can be viewed as multiplication from one term to the next, but it's not the same number every time. It goes by times 2, times 3, times 4, times 5, so it's not geometric. And then this one down here is definitely not geometric. You actually know what this one is. This one's arithmetic because we are adding 3 every single time. So this one here is actually arithmetic because the common difference is 3. We're adding 3 every time to get to the next term. So of sequences that exist, some are geometric. They can be arithmetic. And then we have some that don't fit into either category. We're not going to spend time on the ones that don't fit into this category, either category this year, but there are classes where you could do that. Now, the next thing we want to do is take a look at a rule for the nth term of a geometric sequence. So here's the rule. Usually you'd have to memorize this rule, but since we are doing distance learning, you'll be able to look that up whenever you need it. So that's one benefit today. And we're going to consider this sequence. Please go ahead and fill that in if you printed out the worksheet. So the sequence we're looking at is right here. We want to find the common ratio, write a rule, and then we're going to find a sub 8 or the 8th term. So this sequence is geometric. I can tell because we're doing times 3 every time. So I recognize that that's times 3. I recognize that that's times 3. I'm not really sure about that one. So let me sneak a calculator. And sure enough, 45 times 3 is 135. So that's not something I might recognize, that last one, because they get kind of big. But by looking at one term to the next, we can figure out the common ratio. So the common ratio is 3. Now for a rule for the nth term, the formula says it's the first term times the common ratio to the n minus 1. So the rule is going to be the first term, which is 5, times the common ratio, which is 3, to the n minus 1. You cannot make that 15. You'd be breaking PEMDAS. According to order of operations, exponents have to happen before multiplication. So this is 5 times whatever 3 to the n minus 1 is. And if we want to find a sub 8, we're going to go in here and plug in 8. So we're going to have to put this into our calculator, I think, unless you want to figure out what 3 to the 7th is, and then multiply that by 5. So let's use a calculator for this one. So it's 5 times 3 to the 7th. The graphing calculators do PEMDAS for you, so you can put it in all at once. The calculator is going to do the exponent, and then it's going to do the multiplication. And we get this very large number. That's one thing about geometric sequences is depending on the numbers you have, they can actually get a lot bigger, a lot faster than the arithmetic ones that you've seen in the past. So what I'd like to do next is I'd like to take you back over to Desmos and just show you why this topic is in chapter 6. So let's do that now. Okay, so we're over in Desmos now. Let me get rid of the points from our previous example with that arithmetic sequence that gave us a line or a linear function. And let's plot the points from the numbers that we have here. The first term is 5, the second term is 15, third term is 45, the fourth term is 135. And if you notice, you really can't even see that because I need to see up higher in my viewing window. So I'm going to go in and actually make an adjustment here to go up to at least 135 so that we can see up higher. And now we can see more of the points on our graph. So down here is the x-axis, and these are the points on our graph. And when you look at those, they're not linear. And if you look at them, I think you might see what they are. They're exponential. So that's why this is in chapter 6. Geometric sequences are not the same thing as exponential functions, but they're related. Because if you look at the structure of this, if I replace a sub n with y and I replace n with x, you can see that what you have is a transformation of an exponential function. So when you look at that purple graph over here in Desmos, it's the same thing as 5 times 3 to the x minus 1. It's the 3 to the x graph moved right 1 and with a vertical stretch of 5. So again, geometric sequences are not the same thing as exponential functions, but they're related, and that's why it's in this chapter. At this point, we're just going to continue our work with geometric sequences in series. I'm not going to take you over to Desmos again, but I find it interesting to find out why this topic shows up in chapter 6, so I thought you might be interested as well. Before we go to the next problem, I just want to look at this one a little bit more, because we went ahead and found the 8th term by doing 5 times 3 to the 7. And I just want to show you that, or remind you that these numbers are going to get very large very quickly. So if we wanted to find the 15th term, since n would be 15, 15 minus 1 would be 14. So that's the 14th term, very large number. And if we wanted to find, for example, the 8, if we plugged in 18, we'd be finding the 19th term, because picture plugging in 19 for n. This would become 18, right? Or if you want, I can actually make it 19 minus 1 so you can see the structure. So this will be the 19th term. And then here comes the 20th term. This is now so large. And here comes the 21st term. This is now so large that the graphing calculator resorts to scientific notation. This E10 means times 10 to the 10th. And if I go ahead and make this even bigger, if I put in like 24 and find the 24th term, this means times 10 to the 11th. So what you'd have to do to find this number is move that decimal point 11 places to the right. It's huge. So what happens is these numbers get very big very quickly, and that's why you find we do a lot of calculator work when we're doing geometric sequences in series. Now let's go to number 2. If you printed the handout, you're going to have to write down the sequence, because I left that out. And let's go through the same process. First, this is geometric, because if we look, we are multiplying by 1/2 every single time. I know you might look at that and think dividing by 2 instead. I do as well. But when we're looking for a common ratio, it's what do we times by to get to the next term. So the common ratio is 1/2. The rule for the nth term, you can look at your notes here to get that general structure. And then we're going to plug in a sub 1 with our first term. And then we're going to do r is going to be 1/2. And that's to the n minus 1. I went ahead and put 1/2 in parentheses because I want it to be nice and clear that the entire fraction is being raised to the n minus 1 power. That's it. Now to find a sub 11, we're going to plug in 11. And instead of putting 11 minus 1 in my calculator, I think I'm just going to go ahead and simplify that and make that a 10. So let's go ahead and do 16 times parentheses 1/2 to the 10th power. And that's what we get. It's a very small decimal. So this is 0.015625. And that might be just fine with some of you, but personally, I like fractions better than decimals. So just to remind you, or just to show you, if you hit the math button right here, when you have a nice decimal like that, that very first thing, when you hit math, it says a little like triangle and fraction. That's going to convert your decimal to a fraction. So we're going to take the previous answer, convert it into a fraction, and that's 1/64. So for anyone who thinks that looks nicer, that's a quick way for your calculator to help you out. It can convert the fraction to a decimal for you. And I'm going to pause for a second, time out, because a lot of times people say, oh my gosh, I didn't know you could do that. So just to show you, like if you had, I'm just going to make one up, this right here, if you hit math and then frac, it'll convert this to a fraction and it'll reduce it for you as well. So it's not going to write 684/1000. It's going to go ahead and reduce it. And it can even do that with when it would be a mixed number, so something larger than 1. And this is going to give me an improper fraction of 63/10. So just in case you never knew that, your calculator could do that for you. The one thing it can't do, just so you know, is if you have something like square root of 2, remember that that's irrational. So that decimal never actually ends and it's not repeating. So if you tried to use the calculator to convert something that's irrational, it's not going to do it for you. It's just going to give you back the decimal because you can't convert something that's irrational into a fraction. All right. But this here, this 0.015625 that we got as our answer, that can be written as a fraction. And if we write it as a fraction and then reduce it, we end up with 1/64. Okay. So that's either one of those is a good final answer for the 11th term. Let's move on to number 3. For number 3, I have a sequence that has alternating signs. So when you go to look at this, you have to kind of be careful because we are doubling the numbers. 2.5 doubled is 5, doubled is 10, doubled is 20. But since we're alternating signs, we're timesing by -2. And that might be something that you don't see immediately. You might have a thought process on that. So you might first realize you're timesing everything by 2, and then you say, wait, the signs are changing. Let me check it. Here's how you check it. This times -2 is -5. It's working. -5 times -2, it is 10. It's working. 10 times -2 is -20, and so on. So you can always pause for a moment and make sure the common ratio that you found is correct. Now for the rule for the nth term, you can use your notes because this formula is still new for you. Your first term is 2.5. Your common ratio is -2. And we'd have that to the n-1. You do need the parentheses around the -2 here. Then we're going to go ahead and find a sub 10. When you plug 10 in here, it's going to become 9 because 10 minus 1 is 9. And I'm going to go ahead and get set up because when we go to our calculator, when we want to plug in 11, 11 minus 1 is going to become 10. So 2.5 times parentheses -2 to the 9th. And that gives us -1,280 for the 10th term. Now, when you go to find the next term, you can type that whole thing in again or hit second enter. Remember that second enter brings up the last thing you typed. So now all I have to do is go in and change the exponent. It's a little less work. So second enter was how we did that. And what we get here is 2560. I just want to pause for a moment and just have you think, does it make sense that after a negative term, the very next term was positive? Yeah, it should, because to get from this term, this is the 10th term, and this is the 11th term, you would multiply this by -2. Let's check that out. If I take that -1280 and multiply it by -2, I get 2560. Looks good. Now that we've done some work with sequences, let's start to talk about series. A sequence is when you have the list of numbers. A series is when you go to add up the numbers. So here is the formula for the sum of the first n terms of a geometric series, series or sequence, because we're adding them up. So you can say we're adding up the terms of the sequence, or you can say it's a series. And for the arithmetic, remember, it was this formula. So for arithmetic, we have a different formula, and usually you have to memorize both of those. But this year, you're not going to have to because you are going to have open note when we get to the assessment. So for arithmetic, this is your formula. For geometric, this is your formula. The geometric formula looks a lot more complicated, but it actually requires less stuff. For the geometric sum of the first n terms of a geometric series or sequence, all you need is the first term and the common ratio and the number of terms. That's it. For the arithmetic series, you need to know the number of terms, the first term, and the last term. We don't need the last term in this formula. So even though the formula is more complicated, it's going to be a little harder to get it in the calculator. The formula requires less stuff. So let's go ahead and try this one. This one should look familiar. We found before that the common ratio for this one was 3, and the first term there was 5. And we want to find the sum of the first 11 terms. So if we plug into this formula, this is the number of terms, so 11 terms. A sub 1 is first term, which is 5. Big parentheses with a fraction. It's 1 minus 3 to the 11th over 1 minus 3. Now, before we continue, please notice, in this formula, we use n. For the formula for the nth term, the exponent is n minus 1. So you want to be very careful. When you're looking for the formula for the nth term, the exponent is n minus 1. But when you're doing the formula for the sum, the exponent is n. Be careful. Use your notes to help you as you do problems. Now, we need to get this into the calculator. What I like to do is clean it up a little bit first. So I'm not going to distribute the 5 in. That seems like too much work. We can't do 1 minus 3 to the 11th because the 3 to the 11th has to happen first, and I don't know what that is. But I can do 1 minus 3. That one I know. That's -2. So that's a little less stuff to put in the calculator, and this can be the trickiest part. So make sure you grab your calculator and try this with me. So it's going to be 5 times, and then in there, the numerator is 1 minus 3 to the 11th. So it's 1 minus 3 to the 11th, and then we have to divide that by -2. Now, if you notice, when I put this in my calculator, I have more parentheses because we have parentheses around the entire fraction, but because the numerator is 2 terms, we have to have parentheses around the numerator as well. So that's why, see, I opened the parentheses for the big fraction, and then I have open parentheses for 1 minus 3 to the 11th, and then I end up dividing by -2. This is the answer you should get. Now, I think that's a little bit complicated to put in the calculator, so sometimes I do it a little differently. Sometimes I don't put the whole thing in at once. So sometimes what I do is think, if I were going to do this myself without a calculator, what would I do? Okay, well, I think what I would do, let me rewrite this without the pink there, so it's easier to see. Okay, if we were going to work this out, we'd start in the parentheses, right? So we might do 1 minus 3 to the 11th. So you can type just that part in your calculator, and then that's this quantity. What you would do next is divide it by -2, and then finally, you would multiply it by 5. So if you like that better, it's the same answer. And that's actually how I usually do it, because it's really a lot of parentheses to try to put it in all at once. Okay, so if you want to put, and actually, if you want to put this in the calculator, so if you didn't want to do the 1 minus 3, you would need parentheses around the numerator and the denominator. It's a lot of parentheses. So my advice is, why don't you put the numerator in the calculator, hit enter, divide by that denominator, hit enter, and then multiply by 5. We're going to try another one in a minute, so you get to practice more. And that's what we would get. If we add up the first 11 terms of the sequence, we'd be up to 865. 2 more to go. So here's our next one. We want to find the sum of the first 8 terms of this sequence. That should also look familiar. We worked with this one earlier. So we'll need the first term. We'll need the common ratio. We established earlier that that's -2. And the sum of the first n terms, you can look up this formula because you don't have to memorize it this year. And it's brand new, so you would look it up at this point anyway. And if we want to find the sum of the first 8 terms, we're going to plug in the first term for a sub 1. We're going to plug in -2 for r. N is going to be 8. And the denominator is 1 minus -2. So I'm going to clean this one up a little bit. If you want to put the whole thing in your calculator, you can, but you would need parentheses around that numerator and the denominator. It's a lot of parentheses. So I'm going to clean up a little. 2.5 is going to sit out front. You cannot make this minus a negative into a positive. And I know it's tempting. You cannot, because there's an 8 there. There's an exponent. So by order of operations, the exponent has to happen before the subtraction. So you cannot make that minus a negative. For certain numbers, you'd luck out and get the right answer, but for this one, you'd actually get it wrong. Now down here, you can make that minus a negative a positive because there's no exponent in the way. So this is 1 minus -2. That's 1 plus 2. We all know that's 3. This is not the same because of the exponent. So when there's an exponent there, you can't just cross out the minus and negative. So what we're going to want to put in our calculator is this. And there are some other shortcuts. You could do some other work with that before you use a calculator, but I think that's where most of you are going to be comfortable going to the calculator. So you have the 2 options. What I would do personally, and this is actually how I do it, this is what I would do, is I put the numerator in. Because if I were going to simplify this by hand without a calculator, I would work on the numerator first because it's inside the parentheses. So 1 minus -2 to the 8th. And then I hit enter. Now with that value, the next thing I would do is divide by 3. And now that I figured out what's inside the big parentheses, I have to multiply that by 2.5. And what I get is -212.5 or -212.5 if you prefer. Either way is fine. If you want to put this entire thing in your calculator at once, what you'll have to do is you'll have to have these parentheses, but then you also need parentheses around the numerator. And I just think that's pretty hard to keep track of, because once you're finished with the numerator, you'll have to close that first set, then divide by 3, and then you have another parentheses. I think that's a lot of work. Same answer. Okay, so taking a look at this, I just want to see what you think. Does it make sense that this answer came up negative? Well, let's look at what we found. So this is a little extra information. So what we just found is if we have the sequence and we add the first 8 terms, here are the first 8 terms. What you get is you get a total of negative 212.5. And what actually happens here is because you have, see all these negatives, these are all negative, and these are all positive. So by the time you're all done adding all those up, you have a negative left over because the negatives add up to more than the positives did. And what's kind of interesting is this is the sum of the first 8 terms. So even though it doesn't ask, I'm going to ask us to take a moment and find the sum of the first 9 terms. And that denominator, by the way, is still going to be 1 minus negative 2. So I'm just going to make that a 3. So go ahead and get that into your calculator, see what you get. You should get 427.5. Since I had it lined up, I just went ahead and changed the exponent to 9. But what I would normally do is numerator, hit enter, divide by the denominator, hit enter, multiply by that number out front. Same answer. Okay, now you get 427.5. Does it surprise you that the sum of the first 8 terms is negative, but then the sum of the first 8 terms, 9 terms, becomes positive? Well, let's take a peek. This was the sum of the first 8 terms. I was going to write that out in words, but we have a notation for that. That's sum of the first 8 terms. Now look at the sequence. What would the 9th term be? If we had 40, we multiply by negative 2 to get negative 80. We multiply by negative 2 to get 160. We multiply by negative 2 to get negative 320. The next term would be this times negative 2. That's 640. So if these added up to that negative, and then I add 640, check this out. So this is the sum of the first 8 terms. So if I add up the first 8 terms, I get this negative 212.5. And if I add just the very next term, which is the 9th term, there we have 427.5, the same thing we got with the formula. So just kind of interesting. Like I said, this is a little extra information. You don't have to even write down this part, but I think it's worth seeing, especially when the signs alternate, that your sums are going to alternate as well. So the sum for the first 9 terms becomes positive. So if we were to add up the first 10 terms, we'd be back to a negative because the next term is this times negative 2. The next term is negative 1280. So when you incorporate that, you're going to end up back with a negative sum. And just to show you what it would be, you end up with negative 852.5. Okay, last problem for today. We have to do one in sigma notation. So this is uppercase sigma. It's a Greek letter. Lowercase sigma looks like this. It looks nothing like uppercase sigma. And that means we're going to find the sum. So starting with the first term, we're going to add up all the terms all the way up to and including the 8th term. So for our first term, this is our rule. Do you recognize that it looks like the geometric sequence rule? Because the geometric sequence is first term times the common ratio to the n minus 1. So see how that kind of lines up? Because there's an n minus 1 exponent, there's a number that was being raised to that, and there's a number out front. So this is geometric right there. But we can plug in to find out. So if I plug in 1, doing PEMDAS, 1 minus 1 is 0. 4 to the 0 is 1. So my first term is 7. See how that lined up before? So my first term is 7. So if you recognize that this is that format for the geometric geometric sequence rule, you can actually just go ahead and pick out that the first term is 7. Can you tell what the common ratio is? Common ratio is 4. But let's go ahead and find the second term kind of formally by plugging in. Right here, we're going to plug in 2. 2 minus 1 is 1, and 7 times 4 is 28. And do you see here, to get from 7 to 28, you multiply by 4. And we actually don't need to do anything else. We don't even need to find the 8th term. Because remember, for geometric, all we need is the first term and the common ratio. So we actually didn't have to do any of this work at all if we recognize that this is geometric, and we can figure out that 7's the first term and the common ratio is 4. And that's going to take some practice. I don't expect you to be at 100% with all this right now. This is the first day of geometric sequences and series. So to find the sum of, we're looking for the sum of 8 terms. It's going to be the first term times the big fraction with 1 minus the common ratio to the 8th over 1 minus the common ratio. And I shouldn't bother putting a r there because I actually know the common ratio is 4. And you can go straight to your calculator from here, but I think that's kind of difficult. So I'm going to clean up a little bit. The denominator is -3, and I feel comfortable putting that in my calculator. So I'm just going to do it my normal way. And like I said, I hope you took out your calculator and you're trying this, because this can be the hardest part. And we get 152,915. So if you add up the first 8 terms of that sequence, you end up with 152,915. These terms add up fast. So if you add 728, the next term, and you add up the first 8 terms, you're already up to 152,915.